So we defined the derivative using a limit. We can use that limit to derive several algebraic and non-algebraic derivative rules. For now, we're going to look at 6 algebraic derivative rules, and I'll provide proofs for some of them. So we have algebraic derivative rules. We're going to put them in a chart. Well, I put them in a chart. And they're all going to have names. I mean, the first one, I guess I kind of included in that over there. But remember, the derivative is a new function given a function. So we have an original function and a derivative. Function is c, a constant. The constant function has derivative 0. So I'm going to talk about these 6, prove a couple of them, and then we will look at some examples where we use them. But the first one says the derivative of a constant is 0. The next one, derivative of x to the n. So x will be our variable for all of these. I didn't write f of x for any of them because I didn't want too many x's in the way. But if we have x to the n, n can be any number. X to a number. Derivative is given by n times x to the n minus 1. So derivative of x to the n, bring the exponent down, multiply, subtract 1 from the exponent. Derivative of x to the n x to the n minus 1. So for example, if n equals like 4, then the derivative of x to the 4 would be 4 times x to the 4 minus 1. So 4x to the third. And again, we're going to look at examples of all of these after we cover some of the proofs. This second rule, because we have a power function, we call it the power rule. Derivative of x to the n x to the n minus 1. Next, so for f and g, I didn't write of x's because I didn't want too many x's in the way. But here we have c times f. C is a constant. Constant times a function. The derivative of a constant times a function is that constant times the derivative of the function. So if we look at this one we call the constant multiple rule. First one you can call constant rule if you want. Here we have the constant multiple rule. So just cover both of those c's. If you cover this c, you have f. The derivative of f is f prime. Well, if you just throw a constant in front of it, then the constant carries through in our computation. The next one, f plus or minus g. So I'll call this sum difference rule. F plus or minus g. Derivative is f prime plus or minus g prime, where the plus goes with the plus, the minus goes with the minus. So the derivative of something plus something else, you can do them one at a time. Derivative of f plus or minus g, f prime plus or minus g prime. You can do the derivative of f, and then the derivative of g, and then put the proper sign between them. Next, this one, here we have f times g. We have the product of functions. And notice the derivative here is not given by f prime g prime, which would parallel the sum and difference rule where you just do it one at a time. Here, the derivative is not f prime g prime. It's a different formula. It is f prime g plus fg prime. So you take the derivative of one, multiply by the other, and then take the derivative of the other, multiply by the first function. So derivative of fg is f prime g plus fg prime. We call that the product rule. And down here, we have the quotient rule to take the derivative of a quotient, f divided by g, where of course the bottom isn't 0 because it's not defined if the bottom is 0, but I'm not going to write that to litter up the chart. So f over g, the derivative. Notice again, it's not f prime over g prime. We have a large quotient. We have gf prime minus fg prime all over g squared. So we have a large fraction as our derivative of a quotient. Bottom, derivative top, minus top, derivative bottom over bottom squared. And we call that the quotient rule. So before looking at some computations, let's prove some of these. I'm not sure how many I'll prove. Let's start, and then we'll see where we end up. I'm definitely going to prove product. I'm definitely going to prove sum and difference. I don't know, maybe I'll do all of them except the quotient. How would we prove these? So let's say sum proofs. So the first one, let's do the first one. So maybe I should have just said constant, or I'll say constant rule. How would we prove it? Well, let's take f prime of x. F of x here is a constant. Limit h approaches 0, we'll use that definition. F of x plus h. Our function here, it's the constant function. I just walked into my radiate. F of x is the constant function. F of x equals c. So f prime of x, limit as h approaches 0. F of x plus h minus f of x all over h. F of x plus h is still c. Minus f of x is still c. All over h. How do we take this limit? Well, limit h approaches 0, not x approaches 0. The numerator simplifies to 0. 0 divided by h is 0. Limit as h approaches 0 of 0 is 0. I'm going to do the power rule in a moment. Yeah, I guess I'll just do it next. Power rule is actually more difficult to prove than the constant rule, the constant multiple rule, and the sum difference rule. And arguably more difficult than the product and quotient rules. But let's look at this. Should fit here. F prime of x, limit h approaches 0, f of x plus h. Well, if f of x is x to the n, f of x plus h to the n. Minus f of x, all over h. How do we expand x plus h to the n? Well, maybe I should erase up here. I'll show some side work up here. How would we expand that? If I asked for a proof of one of these, it would probably not be the power rule and it wouldn't be the product rule, but I could reasonably ask a proof of constant multiple, or sum difference. But how does x plus h to the n simplify? Well, let's look. Let's look at n equals 3. N equals 3. Let's look at what happens when n equals 3. We did this in the definition of the derivative video. When n equals 3, what happens in this numerator if n equals 3? Well, we have n equals 3. That expands to this. Subtract x cubed, and you subtract x cubed. So when n equals 3, the numerator, which is x plus h cubed minus x cubed, here's x plus h cubed, subtract x cubed, the numerator would equal just that. So the numerator would equal that, and how would we simplify? Well, all of these terms have an h, and that is what is important. when you expand x plus h to the n, you'll always have this situation where everything has an h except the leading term. But that leading term would then be canceled down here. And what you'd be left with, I should get my blue marker, what you'd be left with is all of these remaining terms over here. Then what would happen? Well, you divide by h. What happens when you divide by h? It simplifies to that. And what happens when h goes to 0? When h goes to 0, that doesn't change. And these both go to 0. And what are you left with? Well, where did this term come from? It came from here, which came from here, which came from here, which came from that second term in the expansion. So let's generalize that to n. Debating what I want to say about the constants. So it equals limit h approaches 0 of what? Well, x to the n plus n minus 1. No, plus n. In the nth row, the second number is n. So the first two terms would look like this, x to the n. Remember, the exponents go x to the n minus 1, x to the n minus 2, and so on. The h's go h to the 0, h to the 1, plus, I don't have much room here. I'm not going to have enough room over there. I want to leave that up there. Sorry. I should have foreseen this when I started in the middle of the board. So, I apologize for this board organization. This equal sign is going to bring us up here. Much easier with a 20-foot chalkboard to do this. I'll explain that column symbol in a moment. So we expand this, we get x to the n, then we get n minus 1, right, then we get n, x to the n minus 1, h to the 1, and after that we get, maybe I won't even use a number sign. Maybe I'll say plus square filled in h squared plus dot 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 plus h to the n. So all of these other terms have at least an h squared on them. And that is what is going to be relevant. So when we expanded this x cubed term, or x plus h cubed, we had x cubed plus 3x squared h plus something with h squared plus something with h cubed. In general, all of these terms are going to have h to something which is 2 or larger. So x plus h to the n simplifies to that, and the rest we're just leaving alone. Well, what do we do with this? Well, x to the n, negative x to the n cancel. So we're left with an h in the denominator, nx to the n minus 1h plus blob h squared plus up to h to the, not 2, plus up to h to the n. Well, again, we can't take this limit because we'd get a 0 over 0. But we can cancel an h from everything. And we're left with what? nx to the n minus 1 plus blob. We cancel an h there. We have one h left. Plus blah, blah, blah. plus h to the n minus 1. And now, as h approaches 0, all of those terms go to 0. And the first term doesn't change because it has no h's. So right here, we proved this result actually for only n a positive whole number, or n equals 0, I guess we technically proved it. I'm not going to prove it for other n values. I might mention that once we have a result after exam 1. But what's important is this observation that expanding x plus h to the n using Pascal's triangle gives us lots of terms with h squared and more, and those eventually all go to 0. And the second term is all that's left. And you can compare this computation to the notes from lecture 4.2 when we did one of the examples with x cubed. You can compare them to what we did in the workshop last week when we did x to the 4th. And you'll see all of those terms went to 0. I will not ask you a proof of the power rule, but it is definitely a nice algebraic result. Next, the constant multiple rule. Well, too many f's. No, there are too many f's. Okay, I'm just going to write capital F. So for constant times f, capital F prime is limit h approaches 0 of what? C f of x plus h. C times f of x plus h minus c times f of x all over h. So maybe I'll write c over here. So constant times f. Replace all x's with x plus h. We get constant f of x plus h minus constant f of x all over h. And remember that we had a limit rule which said we could pull a constant out when taking a limit. You can pull a constant out of a limit. And what we're left with is f prime. So this follows straight from the definition. Let's do the sum and difference rule. Well, let's just do the sum rule. And then, well, let's just do the sum rule and then mention how it also applies for differences. Sum, difference, rule. So for f of x equal f of x plus g of x, f prime of x equals the limit h approaches 0 of what? F of x plus h plus g of x plus h minus f of x plus g of x all over h. Limit as h approaches 0 of that. Well, how does this simplify? Well, I'm going to distribute that negative. I'm going to rearrange the top as well. So I distributed the negative, and then I flipped the two middle terms around. And now what? Well, marker? Well, what do we have here? Well, we have a fraction. We can split this fraction into those two pieces. What would that look like? What would that look like? It would look like this. So if we just split the fraction, we would then have the limit of this large sum. But remember, we can do limits one piece at a time, so we can also break it into the one limit plus the other limit. So we split the fraction and wrote it as two limits. Well, right here, this is just f prime of x. And here, that's just g prime of x. If this were a negative, then you'd have some negatives around, and you just have to flip negatives around. And you'd get the same basic argument. You just have to be a little more careful with the signs. Next, let's prove the product rule. So back in week 1, when we were completing the square, we found we found that adding a convenient zero was helpful. We're going to find, for the product rule, that adding a convenient zero is helpful. To prove the product rule, I should say. Adding a convenient zero is helpful. So here we'll let capital F be f of x, g of x, and we want the derivative. Well, what is it? Well, limit h approaches 0 of, let's write it over here. Am I going to have enough room? Yeah, I think I will. So there's f of x, or there's capital F of x plus h. Replace all x's with x plus h. Minus capital F of x. And it's all over h. Now what we are going to do is add a convenient zero. Which zero, pray tell? Well, this zero. No, I have it backwards. Sorry if you started writing. Usually I put myself in the way so that you can't start writing. Sorry about that. It would work, actually, with what I added, it would work out in a very similar way. But I want it to work out this way so I don't have to rearrange terms. So we added 0. Where did we add 0? Right in the middle. Right here, that term is 0. We are adding a convenient 0. There is a branch of math called analysis, real analysis, where a lot of the details are finding a convenient 0 to add. That's all I'll say about it. I am recording myself. But why does this help us? Well, look what we can do on the numerator. If we look at these two terms, they both have something in common. These first two terms both have a g of x plus h. Why does that matter? Well, we can factor it out. These last two terms have an f of x in common. We still haven't simplified this fraction. There's still the h in the bottom, but what we've done is observe that these first two terms have a g of x plus h. These second two terms have an f of x. So we're not exactly factoring by grouping here. We are doing something similar. I mean, it would be factoring by grouping if this square bracketed term were the same as that other square bracketed term, because we could then factor that out. But we're not doing that. But what we can next do is split this fraction, and we'll see how the result follows. What can we next do? Split the fraction. Notice we still have equals and limits. Split the fraction. F of x plus h minus f of x all over h. The numerator is times g of x plus h. So we're splitting the fraction into these two pieces and the other one. So we have f of x plus h minus, maybe I'll put square brackets up there since that's what I have down here. So we have that term, and we're also going to split the limit as we did before. And what do we have here? We have f of x. I'm going to write that on the other side, and no, I'm going to write it there. That's how I wrote it before. So we split the fraction, and look at what we have. Well, let h go to 0 on that one term. Let h go to 0 on g of x plus h. What do you have? You have g of x. We don't even have to let h go to 0. We can just pull f of x out here, because f of x is not impacted by h here. And look at what we have now in those square parentheses. We have the result we wanted. And this is all doable because we added a nice, convenient 0. The first one is f prime of x. Leave g of x alone. The second one is f of x. And this is g prime of x. So we just proved the product rule. The quotient rule has a similar direct proof. I'm not going to go over it. I'll just say quotient is similar. After exam 1, I will discuss an alternative proof for the quotient rule. So right here, we proved a relatively large theorem, so we will put at the end of it a QED. Latin for quod era demonstrandum, and it means it has been shown. In math, when you're done with a proof, you usually put a QED at the end of it, as like an exclamation point. This proof is done. So now we've proved these. Let's use them. So let's go over a couple examples using these. Hopefully you wrote them down somewhere, because I'm not going to write them on the board to use them. I'll just write some examples. So let's do some examples. Find f prime of x. So let's do f of x equals x cubed plus 4. Let's do f of x equals 7x cubed. Now let's do 7x cubed. Part C, f of x equals x. D, we'll probably do 7-ish examples. F of x equals, what have we done? We've done that. Let's do, so we didn't prove for other exponents. Let's assume that that doesn't hold for other exponents. Let's do 5x to the 7th plus 4x to the 2 plus, no, minus x to the 9. E, and we're going to put an F and a G on after this, maybe even an H. F of x equals what? Let's do x to the negative 5. I guess I'll put an F down here too. Part F, f of x equals root x. So let's do these 6 examples, then we'll do, I don't know, 2 more. And I'm going to do this work right across the board for these. But we're going to use those algebraic derivative rules. So the first one, I'm just going to write the answer over here. First one, x cubed plus 4. Well, rule 4 tells us we can do these one piece at a time. Rule 2 tells us how to deal with x cubed. It's the power rule with n equals 2. So remember, for the power rule, the derivative of x to the n is nx to the n minus 1. So if n equals 3, then the derivative of x cubed would be 3x to the 3 minus 1. And what about 4? Well, 4 is a constant. Rule 1 applies. The derivative of 4 is 0. 4 doesn't change as x is changing. Although maybe I should mention that after we do physics applications after exam 1. So using rule 2, we got 3x to the 3 minus 1. Using rule 1, we got a 0. Now we just have to simplify this a little. 3x to the 2. Next. So that was part A. Here's part B. Part B. Well, what do we have? We have 7 times x cubed. Rule 3 tells us that we can pull that constant out and deal with x cubed. So when I use that rule, I like to just write the 7 out and pretend it doesn't exist anymore. So if I wrote the 7, now I have to deal with x cubed. Well, we know how to deal with x cubed. We got 3x squared from rule 2. And then this simplifies to 21x squared. So we have the constant rule here. 7 comes out, and then you have 3x squared, and then you just combine the 7 and the 3. So these first 6 are going to illustrate rules 1 through 4 in our chart, and we'll get to the product and quotient rules later. How about this next one? F of x equals x. How do we deal with x? Well, again, x is a power function because x is x to the 1. Derivative of a power function, x to the n, is n x to the n minus 1. What happens if n equals 1? Well, if n equals 1, what do you get? 1x to the 1 minus 1. It's a lot of 1s. 1x to the 1 minus 1. What does that simplify to? 1x to the 0. What's x to the 0? It's 1. I shouldn't write 1x, 1. 1x to the 0 is 1 times 1, which is 1. So for part C, using the power rule, we got that the derivative is 1. Let's make an extension of part C. No, let's not make an extension of part C. Part E, I'm going to put an extra 7x on that. Part E, I change the function. How about part D? Well, part D, we have 3 things added together. So rule 4 says we can deal with them one at a time. And you can add with a negative sign if you want. We can deal with them one at a time. And notice here, we have a 5 in front of x to the 7th. So leave the 5 there and deal with x to the 7. 7x to the 7 minus 1. So 7x to the 6. How about 4x squared? What do we get here? Well, there's a constant in front. So just write the 4 and deal with x squared. What do you get for x squared? Well, if n equals 2, you'd get 2x to the 2 minus 1. What's 2x to the 2 minus 1? 2x to the 1. So 4 times 2x. And what about that negative sign? Well, the negative carries through. And we have x to the 9. If n equals 9, what do you get? 9x to the 8. 9 minus 1 is 8. And then we'll just simplify this. When I say simplify, I really just mean combine the terms and make them 35. And make that middle thing an 8. You don't have to factor out an x. Don't do that. Part E. How do we do part E? Well, again, we have 2 things added together. How do we deal with 2 things added together? Well, we deal with them one at a time by rule 4. The first thing we have is x to the negative 5. Well, again, that is x to a number. X to a number. Derivative of x to the n is nx to the n minus 1. What if n equals negative 5? What do you get? Negative 5x to the negative 5 minus 1. Negative 5 minus 1 is negative 6. And what about the next thing? Well, there's a positive sign there. There's a 7 there. So that positive 7 goes through, and you're left with just x. Well, the derivative of x we saw up here was 1. So we have positive 7 times 1. So you get negative 5x to the negative 6 plus 7. So now we will make a remark. If k, it's more of a theorem, is a constant, then the derivative of k times x is just k. Remember, this is another of our derivative notations. So if k is a constant, derivative of k times x, derivative with respect to x of k times x is just k. And we saw that here. And we also saw that here. And a proof of this remark is by the power rule, because the derivative of x to the first is 1x to the 0, which is just 1. So that's a convenient observation, which it'll show up enough times that you definitely get used to it. And how about part F? Well, x square root of x, there wasn't anything in there that told us how to deal with the square root of x. Or was there? Well, the square root of x, remember, you can write with an exponent as x to the 1/2. And now we can take the derivative of x to the 1/2. What is the derivative of x to the 1/2? Well, derivative of x to the n is nx to the n minus 1. Nx to the n minus 1. Well, if n equals 1/2, what do you get? 1/2 x to the 1/2 minus 1. So it's 1/2 x to the negative 1/2. 1/2 minus 1 is negative 1/2. For now, you can leave that with the negative. In general, you can leave the negative exponent. I am actually going to, after we do a little more, make a remark on this one, because it is one that'll show up a few times. But for now, just use the power rule on that, like that. So let's do two more. We haven't illustrated the product or quotient rule. So let's call them G and H. And then let's do an I guess. Because there are probably a couple more things I'd like to do that I won't be able to fit in the product and quotient one. So part G, part H, find f prime of x. This is going to extend across two boards. For any question where you're asked to find f prime of x, you don't have to simplify beyond, combining like 7 times 5 is 35. So let's do, I already did negative 5, didn't I? Yeah. So let's make this a different number. Let's make it a negative 4. So I'm going to add an H after this and an I. Okay, GHI. G might take up some space. So we have these functions. So part G, I intentionally wrote it as a product. You could distribute this out and do a bunch of power rules. I'm going to use the product rule. You could use the power rule, you'd get the same answer. I'm going to use the product rule. For full disclosure, I frequently mix up the words power and product. Product. We have two things multiplied. When we have two things multiplied, we can use the product rule to take their derivative. Well, what does the product rule say? I'm going to write this down here. So this is part G. Well, it says the derivative of fg is f prime g plus fg prime. So the derivative of the first times the second plus the first times the derivative of the second. So we just have to follow that. So we need derivative of the first. Derivative of x cubed, 3x squared. Derivative of 2x is 2. Derivative of 1 is 0. So right here, these G and H are going to Now they're going to follow in similar ways. Each of the pieces is going to follow in similar ways to A through F. So we have derivative of the first times the second. Well, that's great. So we have derivative of the first times the second. We still need all this. Plus the first, which I'll write a little smaller because I am running out of room, times derivative of the second. What's the derivative of the second? Well, see what you get while I block it from view. (20x cubed) plus 28x to the negative 5. Where did that come from? Well, derivative of x to the fourth is 4x cubed. 4 times 5 is 20. What about the other thing? Well, derivative of x to the negative 4, negative 4x to the negative fifth. Negative 4 times negative 7 gives us positive 28. My guess is that probably half of you wrote a negative 3 here instead of a negative 5. That is a very common mistake to make once. I made that mistake when I first learned these. Whenever I have a negative exponent and I'm taking a derivative, I always pause and make sure I'm subtracting 1 from the exponent. Positive exponents show up much more than negative exponents, and we're very used to going in derivative computations from 4 to 3, like that. So it's very easy to think, well, okay, I have a negative 4, I'm going to go to negative 3. But no, subtract 1 from the exponent. So always, when you have a negative exponent, slow yourself down and be sure you are subtracting 1 from the exponent. So let's look at our answer. You don't have to simplify this. You don't have to simplify it. So we have derivative of the first times the second plus the first times derivative of the second. We have those 4 pieces. Of course, you could have done this first and that second. And you can add whatever order you want. When grading a power or a product rule type question, I do always just look for those 4 pieces. Derivative of 1 times the other plus derivative of the other times the 1. Next, we have a quotient. How are we going to deal with this quotient? Well, we're going to give ourselves lots of space to deal with the quotient. H f prime of x equals. Well, what's the derivative of a quotient? Let's remind ourselves, not equals. Derivative of a quotient, f over g, is what? Bottom, derivative top, minus top, derivative bottom, over bottom squared. Bottom, derivative top, minus top, derivative bottom, over bottom squared. So we just have to follow all of that. We're going to have 5 pieces in our answer. And let's see what we get. Bottom. Okay. Derivative top. So there's bottom, derivative top. Derivative of the top, well, we have some power rules. 15x to the 14. 7x to the 6th times negative 2 gives us negative 14x to the 6th. 7 is a constant, so its derivative is 0. So we have bottom, derivative top, minus top. So just write the top. Derivative of the bottom. What's derivative of the bottom? We have some more power rules and constant rules. 10x to the 9. 7x is a constant times x, so the derivative is just the constant. Minus x to the negative 3. Well, we get a negative 3x to the negative 4, but the negatives make a positive. and it's all over bottom squared. So for the quotient rule, 5 pieces, bottom derivative top minus top derivative bottom over bottom squared. Don't simplify. And usually I say you shouldn't simplify or you don't have to simplify. And that was phrased more in a commanding way. Don't waste your time simplifying this. But do go back and check your answer. Bottom, derivative top, minus top, derivative bottom, all over bottom squared. So now we have this last one. So this last one is forcing lots of power rules with exponents. Or with fractions, I should say. Power rules always have exponents. So try this, see what you get while I write my answer a little lower so I'm blocking it. And then I'll explain the answer. So you might want to pause now and not look at the answer, or do whatever you want, because I'm going to explain this answer now. So we have 3 things. We can take the derivatives one at a time. And how do we do that? Well, x to the 5 halves. These are all going to be power rules. So we need for each one nx to the n minus 1. So what's 5 halves? Well, it'd be 5 halves x to the 5 halves minus 1. What's 5 halves minus 1? Well, if you have $2.50, you spend 1, you're left with $1.50. Or you could say 5 halves minus 2 halves is 3 halves. How about for the next one? Well, for the next one, n equals 1/3. So you get 1/3 x to the 1/3 minus 1. What's 1/3 minus 1? Well, 1/3 minus 1, 1/3 minus 3/3, so negative 2/3. And for the last one, notice first, the negatives again are going to cancel out and make a positive, in this case, 7/4. Then we need negative 7/4 minus 1. What's negative 7/4 minus 1? Well, negative 7/4 minus 1, negative 7/4 minus 4/4. So negative 11/4. So work on these examples. But before we finish, let's make a remark and let's do an example with 2 parts. And I need the exact equation I wrote here to make that example make sense. Well, let's do the equation since I'm loading the paper, and then let's make the remark. So we're going to have an example with 2 parts, an application. Example. Let f of x equal x cubed minus 7x squared plus 8x plus 3. Okay. Part A. Find an equation for the line tangent to f of x when x equals 2. Part B, at which x values does f of x have a horizontal tangent. So first one, we want an equation for a tangent line. Second one, we want the x values at which the function has a horizontal tangent. Well, for part A, for an equation for a tangent line, we need a point and a slope. Well, the point is given when x equals 2. What do we get when x equals 2? Well, f of 2 is 8 minus 28 plus 16 plus 3. So what did I say? 8 minus 28 makes negative 20, plus 16 makes negative 4, plus 3 makes negative 1. So point is x equals 2, y equals f of 2, and f of 2 is 8 plus 19, 27 minus 28, so negative 1. How about the slope? Well, the derivative, remember, gives us the slope of a tangent line. So we need here f prime at 2. Well, I don't see f prime written anywhere. I don't see f prime written anywhere. So let's find f prime. Well, we have a bunch of things added together. Do them one at a time. Use some power rules. Use some constant rules. Derivative of a constant is 0. Derivative of 8x is just 8. Derivative here is negative 7 times 2x. Derivative there is 3x squared. And f prime at 2 equals what? Well, substitute x equals 2. Look at that. Negative 28 shows up again. F prime at 2 equals what? 3 times 4. 14 times 2 negative. So f prime at 2 is 12 plus 8 minus 28. So negative 8. And now an equation for the line is y minus the y value equals slope x minus the x value. So we needed a point and a slope. We use the function to find the point, and we use the derivative to find the slope. Next, at which x values does the function have a horizontal tangent? Well, remember what a horizontal tangent looks like. A horizontal tangent looks like that, or it looks like that. So for part B, I'm going to be lazy. For part B, what we need is where the slope of the tangent line is 0. So we need where the derivative is 0. And, well, how does this factor? Well, let's see. We have, we need what? An 8 and a negative 14, so 4 and 2 make 8. Negative 2 and negative 12 make negative 14. So we get what? X equals 2/3 and x equals 4. Give us our horizontal tangent lines. So there are just two of the things we could do with the derivative. But for now, I'd just like to make one more remark. The following are useful to, how about this sentence? The following are useful to get to get used to. The following are useful to get used to, meaning throughout the semester it will be convenient to have these derivative computations quick in your mind. Derivative of square root x is 1 over 2 square root x. There's going to be a second one in this list. Derivative of square root of x is 1 over 2 square x. We actually already saw this written in a different way. So refer yourself to example, I believe it was F, where we did the derivative of square root of x using the power rule. So right here, for 1, using the power rule, going from square root of x, using the power rule, we got half x to the negative half. How does that simplify? Well, negative exponent just goes in the other side of the fraction. Half exponent, half as the exponent, is just the square root. This next one we did not see, so we'll look at it now. So what do we have? We have 1 over x, derivative negative 1 over x squared. Where does that come from? Well, I would not recommend quotient rule, because 1 over x is just x to the negative 1. And the derivative of x to the negative 1, using power rule, is negative 1 x to the negative 2, which equals negative 1 over x squared. Now, if you're just told, find the derivative of something, and it has the square root of x, and you wrote that as your answer, that would be okay. That would be correct, full credit. If you had one, find derivative of 1 over x, and you said negative x to the negative 2, that's okay and correct. Now, I'm just including this remark here because there will be in Chapter 4 several applications we do. And in those applications, these derivatives will show up a few times. And because of that, and in these applications, we're also going to be doing more than just finding the derivative. We're going to be using the derivative, doing algebra using the derivative. And because of that, it's very convenient to jump over the power rule arguments and jump straight to these fractions. So, just keep these in mind. For now, power rule will be perfectly okay, but as we go through the semester, we will find that immediately writing them as their fraction, or in their fraction form, is much more convenient. And remember here, we have the derivative notation, the derivative with respect to x of that on the inside. So try the computations. After exam 1, we're going to extend our derivative rules to trig functions, inverse trig functions, exponentials, logarithms. But for now, just practice using these 6 rules. They're very, very important. They show up all over the place for the next 6, 7, maybe even 8 weeks.